Hello, class. I I think I'm recording. Pretty sure that I am recording. Everything seems to be there. First lecture of the day today. I'm hoping to get. I think I got like 3 or 4 lectures done yesterday. And of course, I want to go over this stuff, and I sort of teach it, a different way every time because it depends on who the audience is and what I think they can handle and everything else. And so that's why I'm going slow with you guys. I'm kidding. Of course I'm not. I'm going very fast, but you can always go back and look at it. Another thing that I've done, I'm getting better. The studio's getting better every day. You probably noticed it's a little brighter. And because it's brighter, it also doesn't seem to lose the focus as much. I know, you think that this just happens. Yes. Well, us in show business, we do a lot behind the scenes, me and Ben Affleck. Yes. Okay. Well, yeah, Matt Damon and Mark Wahlberg, they'll be stopping over later. But right now, I think what we have to do is work on electromagnetic field theory. And so what I want to look at right now, we're going to do several things. Oh, look at that. I'm even, started it a minute late or whatever, but that should still be fine. Now, what I want to do today is we're going to look at the voltage calculations for a 2 line system, like, transmission line, and look at the voltage profile of that. We're also going to look at the derivation of the capacitance per unit length for a coaxial cable. And I sort of hate to do this because, like giving you guys snippets of the future, but I'm going to. I'm going to give you guys some snippets of the future. We'll see what we get through, what we don't get through with this today. But this, oh, that is a good pen. They get dull after a while. This is what's called the communications circuit. And you can see how the communication circuit goes. Think of a 2-wire system, this being my signal wire, right, like for a coax, and this being my ground wire, right? And then the signal is propagating along this. And what we really have here is we have R prime, C prime, L prime, G prime. Now, why is the prime on there? What does that prime mean? Well, let me give you, for instance, C prime is going to be farads per meter. R prime is ohms per meter. L prime, henries per meter. And G prime, now you might see that's a resistor there, but really what we're talking about is we're talking about conductivity, right? And I'll explain all of those to you in just a second. We're not really getting to this for a while, but I am going to derive this farads per meter for a coaxial cable, and we're going to be looking at metallic conductors. So coaxial cables are definitely a subset of those. And it's probably the one that's most intuitive, that people are most aware of, is coaxial cable. It comes to the back of your TV, all the time. So this is actually moles per meter, because we're talking about conductance, we're not talking about resistance. Later on, when we start talking about transmission lines, what I'm going to say is that this here, for most modern transmission lines, we can assume that G is 0, very close to 0. In everything that we do in this course, we can really assume that G is 0. And why can we really assume that? You know, I'm getting a little ahead of myself, but I want to point that out. Why can we assume that? This is my signal wire, right? So in here, I've got a radius A. So in the very center of that here, let me that's more. I don't know even if that's to scale, but I'm going to draw a coaxial cable over here that's not to scale, just so that you can see the radii that I'm drawing. And even that's not easy, but that's going to be for the radius of the inner. The radius of the inner conductor is A, and the radius of the outer to the outer ground shield is B. They're radii. They are not diameters, right? Now, they would be in the same ratio. Radii would be in the same ratio as diameters, but there's other things that you're going to be doing in Chapter 8. So I want you to realize these are radii. Okay. Now, when we look at this coaxial cable, what are we really talking about with these 4 different variables that we have here? Let's take G first. And let's look at what's in between that inner ground shield, right? And that, or the outer ground shield and the inner signal wire, right? Because there's my outer ground shield, and that's made up of braided tensile strength aluminum fiber. If you've ever cut a coaxial cable in half, you've seen that. It's very strong tensile fibers that are then wrapped into a weave, so that they're a braided fiber that goes around that. And I'll talk about why they changed it from the tin foil. You can still find some very old installations where the coaxial cable doesn't have braided aluminum. Instead, it just has tinfoil aluminum. And of course, that's illegal nowadays. It has to be braided aluminum at tensile strength. And I'll talk about that, why that is later on when we start talking about Chapter 8, because this is not really, Chapter 8. I'm just pointing out some things now to give you some conceptual understanding of what C prime is before I derive it. Now, let's think about this. This is always going to be 0 volts. But that signal wire inside is not always going to be 0 volts, is it? In fact, if we were to look at an oscilloscope of what's going on in that signal wire relative to the outside ground shield, we would see something like this, wouldn't we? Right? Something is going on, some signal is coming down there, and that's changing. That's changing the voltage. And that's a conductor, and that's a conductor. And in between the two is a dielectric insulator, foamed polyethylene. That's right. This is foamed polyethylene. Right? And you're probably saying, oh, Professor Grenquist, what's the relative permittivity of foamed polyethylene? And if you are thinking that, then you are bizarre. But it's 2.38. Now I've put a thing in there. I'm going to write it down here. Epsilon sub r for foam polyethylene is 2.38. And I know you're pulling your calculators out right now and finding the square root of 2.38 so that you can divide the speed of light by it and find out what the propagation speed of the wave is down the coaxial cable. And yep, it's 195 million meters per second. All right. Now, here's what I'm saying about G. let's just talk about G so that we can just get rid of G for good. Is there any current leaking from the signal wire across this insulator, across the insulator to the outside ground shield? No, no, there isn't. You know, foamed polyethylene is such a good insulator. There's no current leaking through here. Now, is there such a minor current? I mean, back years ago, would we have to actually use G in the telegrapher's equations back in the 1800s? Yes, because we're transmitting through the atmosphere that could be very moist and humid, right? So G then between two wires going through the atmosphere, you know, might actually have a significant, even though that would even be small, a significant value. But nowadays, and everything that we're going to be doing in this class, this and really with modern metallic conductor technology, G just doesn't exist. Plastics are such good insulators that G we can really say is approximately zero. In fact, negligible, if not zero. Now let's look at the other ones. Let's look at R prime, C prime, and L prime. Okay. Now C prime. C prime would be in farads per meter. Why is there a C prime at all? Why do I have, well, I've got a different voltage on this plate and I've got a different voltage on this plate. Isn't that the same as a capacitor? If I had a capacitor and I had one plate that was 200 volts and I had the other plate that was, of course not connected to the capacitor, but was a plate there separated by a dielectric, just the exact same as the coaxial cable, right? And the other side of that copper plate, on the other side of that dielectric was 0 volts, just like I've basically got here, except the internal is 200 volts. But I'm just trying to demonstrate what's going on here. That would be a capacitor, wouldn't it? So why isn't this a capacitor? It is a capacitor, and the capacitance in the coaxial cable has a lot to do with the propagation constant of the waveform through the coaxial cable. So that's why we have to look at C prime. And I'm just going to let's derive C prime right now. Okay. So let's say that I'm looking at the electric field around the signal wire that I've got there. So for an electric field around the signal wire, the magnitude is going to be rho sub L. The reason I want to put L there, and I want you to, I know I didn't do it in the last one, but with wires, we're talking about linear density, and you're going to see a sub L there, so I'm going to put it in there. Of course, last time when we were working on that, the only density that we even knew was line density. But now we're going to start to get into surface density, volume density. So, and of course, surface density, the difference between that and linear density is that this would be coulombs per meter, right? Whereas surface density would be coulombs per square meter, and then volumetric density, charge density, would be coulombs per cubic meter, right? So this is coulombs per meter. And so we know that the electric field for that line is going to be the line charge density divided by 2 pi epsilon r, right? And of course, that would be in the radial direction. So if I wanted to find out the voltage at that point, we have the equation minus, and what I'm going to do is, of course, just because I put the minus there, if you remember when whenever I put the minus there, I've inversed the boundaries here. So this would be A to B, or B to A because of the minus. We could switch it around and make it A to B and get rid of the minus, but you know, since I started off with the definition of voltage using that minus sign, which really just you know, shows that the work against the work in an electric field would be positive working against the electric field. Why don't I just write that over here? Positive work in an electric field would be working against the electric field. Okay, let's put a box around that. And you're probably thinking, oh God, what does that mean? What it means is if I have positive work, right? Let's say that I have a positive mass and I start carrying it up a mountain. Am I carrying it against the gravitational field? Because the gravitational field is pointed toward the center of the Earth, isn't it? So in a gravitational field, positive mass creates work against, you know, the field. So as I carry that positive work against the magnetic field, which is pointed toward the center of the Earth, let's say I'm carrying it up a mountain, that's going to give me positive work, right? We all know that, force times distance as I carry it up the mountain. Now, does it matter if I climb a ladder straight up the mountain or if I walk around the mountain on a mountain road? No, it doesn't matter how I get up the mountain. The work, right? The work is force against gravity times the distance in the y direction, right? Isn't that what we've got? If I'm climbing a mountain and I'm carrying a cinder block, why would I do that, for one thing? But if I was, as I go up the mountain, doesn't matter how I get up the mountain, but as I go up the mountain, the distance in the y direction is the only thing that I'm really working against, isn't it? So that's the work that we have here. And isn't that the same for a positive charge working against the field, right? So if I'm trying to push a proton, let's say that I'm in that electron gun that we've talked about, you know, several times, and we did that example of. So I can't remember what it was. I'll say 5,000. 5,000 volts, 0 volts. So now, if instead of having an electron, I had a proton that was moving through there. First of all, if it was just left to move naturally, it would work against this. But what if I forced it? What if I hit it with a sledgehammer and I forced it toward the 5,000, right? Isn't its inclination to go toward the 0, right, for the proton? Because a proton, unlike an electron, wants to go to the more negative, right? It follows the lines of force, right? It's being pushed away from the 5,000. Now, if instead I could somehow attach a rocket to this proton and push it toward that 5,000, wouldn't I have to do work to get it uphill? And that's all I'm saying right here. Now, let's get back to this. So we've got the voltage. That's all set up. All right, now let's go and stick our actual field in there. So I have minus, you know what? Why don't I just change it into a plus? I'll switch it around. So I'm going to say that now it's A to B. So we just put a plus there because that probably makes it easier. And you know, where are we really going, right? This is what I'm talking about, from the surface of A to B, right? I want to find the voltage between the inside wire and the outside wire. That's what I'm trying to do. Okay. Now, let's say, first of all, uh, we know that we've got the charge density. I'm going to write the charge density like this. I'm going to say it's Q divided by L, right? Isn't that coulombs per linear meter? Coulombs per meter, and isn't that what rho is coulombs per meter? And so I'm just going to write it like that: coulombs per length, right? So I take all the coulombs in the whole wire and I divide it by the total length of the wire, and that's going to give me coulombs per meter, which is the density that I've got there anyway, right? So I'm just going to write rho like that. And then I'm just going to put in the bottom what I had there, 2 pi epsilon times r. Okay. And then what I want to do is I want to take this, and so that's this. So this right here is this right here. Now what's dl? Well, if we're looking in the, I did this the other day in a lecture, we know that dl is just going to be r hat dr, right? Because it's in the radial direction anyway already. I hope I didn't lose anybody there. I'm just putting that there, and of course that's dr. So no, everything seems fine. Oh, I might want to rewrite this. I'll rewrite it in a second. Let's just go to the next step, and then I'll simplify the fractions and everything that I've got there. So I've got Q over L divided by 2 pi epsilon. And then I've got to integrate 1 over r from A to B, 1 over r dr. Okay, I should probably put a line down there so that people realize what's in what. Okay, and I think everybody can see that 1 over r dr is just natural log of r, so it's natural log of B minus natural log of A. Should I actually write that out? I'm going to simplify this too. I'm going to say that that's Q divided by 2 pi epsilon. I'm going to take the L out of the numerator and put it into the denominator. And then I'm going to take that, I'm going to put brackets around it, even though I could put parentheses or whatever. I'm going to put brackets, and I'm going to put the natural log, because it's multiplied, of B over A. Right? So that's what my voltage is going to be for that. And I've got Q there. But we know something, don't we? Right? We know that C equals Q over V. If you don't know that, you should know that. And you're going to know it by the end of this course if you don't know it now. That's right. Capacitance is charge per unit voltage, isn't it? Well, if that's capacitance, let's see, Q over V. Well, if I have V, I bring V over there, and I bring this over here, then I could say that Q over V is going to be 2 pi epsilon L divided by, wait, am I getting this right? Q. Yeah, No, that's right. Um, wait a second. 2 pi, yep, epsilon. L. Yep, over the natural log of B over A. I'm sorry about that. It was trying to just, so, for some reason it looked upside down, but of course it's not. Then I looked at my notes, I'm like, no, of course it's not upside down. That's exactly what it is. So of course that equals capacitance, right? So for the capacitance for the whole line, but I don't want capacitance for the whole line. I want capacitance for the line divided by the length. So I want capacitance per unit length of the line so that I can come up with an attenuation that's per unit, per meter. I want to find out how many, how it's going to attenuate per meter. Then I could just multiply it by how many meters of line I've got, and I'll find out what the attenuation for that at whatever frequency I'm broadcasting through that is going to be. So I got C over L, and so if I take C right here and I divide it by L, I think everybody can see that I get 2 pi epsilon divided by the natural log of the outside radius over the inside radius, right? Does everyone see that? Okay, now why? Let's talk about the other two, the R prime and L prime. Now R prime, why do I have resistance per unit length along this wire? Because it's made out of copper, made from, this is for the signal wire, copper. Now the signal wire is usually copper in a coaxial cable, but the outside ground shield is always made of aluminum. And that's because we've got a lot more surface area out there. We don't need as good of a conductor on the outside because we've got so much surface area. Copper is about twice as good a conductor as aluminum. And this isn't pure electrical aluminum out here. This is tensile aluminum, which is still highly conductive and great for a ground shield. But the reason that they've got this out here is because it also is used for people trying to escape burning buildings. That's right. There is a great video on YouTube that shows a woman who is trying to escape from, I believe it was the 4th or 6th floor out of a burning building in New York. And she has her baby in her arms, and the apartment's on fire, and the ladder, you know, from the ladder truck is coming straight up to the woman, but she can't wait. And so she's hanging out of her window, right, by the coaxial cable. Now this was back in I think the 70s or early 80s at that time. And of course, coaxial cables at that time did not use braided tensile aluminum in the outer ground shield, did they? I might have already told you this. And then what happened was it was just aluminum and rubber. I mean, aluminum foil and rubber, right? So she's hanging out there with her baby, and just as the ladder's getting up there, she falls. The cable breaks, that she starts falling, and the guy on the end of the ladder, the fireman on the end of the ladder, holds onto the ladder with one hand, grabs her out of midair with the other hand, and throws her and her baby, who she's still holding on to, behind him onto the ladder with one hand. You know, it was like a circus trick. I hope it's still up there on YouTube. But after that, that was the impetus, that being out there, and I don't even think you guys were born at that time, but that made the evening news, as you can imagine. And after that, they immediately changed, because they figured, you know, everybody now has coaxial cable in their house. You're on the 2nd floor, you can't get out. The only way is the window. You see the coax there. What are you gonna do? you are going to tie the coax onto your bed, and you are going to try to use that coax to lower yourself rather than jumping out that window. So basically now they gave everybody a safety rope that has coax inside their house. It's designed to hold up to 180, but it has a safety factor of 2, and that means that it could hold up to 360 pounds for a person that's trying to jump out of a window or a building and lower themselves down with a coaxial cable. How about that? So yeah, that's great. Let me just check the time because we've got another one. Oh, not a lot of time. So it's made from copper, and since it's made from copper, it has a resistivity, doesn't it? Right? Well, I'll put that resistivity, and that's the symbol for resistivity. Also, obviously, the symbol for that too. So that's probably not a good symbol. And then L prime. You know, L prime. Is there a magnetic field? Is there a changing voltage? And a changing voltage on the signal line means a changing current on the signal line, doesn't it? And so if there's a changing current on the signal line, that means that there's going to be some induction on the signal line. So that's why that's in series. So that's why all 4 of these. And what is this called? This is called the communication circuit. So I wanted to do that, and I wanted to derive. I might actually go through. I don't know if I'm going to derive it because there's so many different geometries for metallic conductors. You know, we've got the coaxial cable, but then we've also got another one that looks more or less like this. You guys might not be old enough to remember what we call twin lead, but you might have it for a an antenna on your tuner, right? Where it's separated by a plastic spacer, and then you've got a plus and a minus wire. And actually, the waveform, remember, the waveform is traveling in between those two, isn't it? Right? Just like the waveform is traveling inside the dielectric, isn't it? Yes, it is. So the next thing that I wanted to do was I wanted to derive what the voltage is for a transmission line. And I'll just talk about it for a second, but it'll probably be the next lecture up because I only have a few minutes left. So it's going to be, I'll draw it on here, but I'll draw it on the next one too. Let's say that I've got a transmission line. This will be the negative one. This will be the positive one, all right? And right in between those two, I'm just going to drop down that separation. And in fact, I'm going to say that it's equidistant between the two, and that distance right there is S. And this distance right here is also S because it's right in between the two, right? That's S. Now, what I want to do is I want to derive the voltage for any place in space. I'm going to just pick a point here, right? I'll just pick a point right there, and I'll call that the point, right? And now I'm going to define 2 radii. I'm going to define radii 1, R1, which is the distance from the positive wire. And I'm going to say that I've got another one over here, and I'm going to call that R2, right? So if I had 5 volts here and I had minus 5 volts here, then this would just be ground. This would be a ground, central ground plane, wouldn't it? Right in the middle. I think everybody can see that. And so that's sort of why I've chose this anyway. It's right in the middle of the two. Doesn't have to be 5 volts and minus 5 volts, but it's definitely going to be halfway of the voltage between those two. All right. Now I'm hesitant about going through this whole derivation. How much time we got? No. No, I think we're going to hold it there, and I'm going to set this up again, and we're going to start from here on the next lecture. That'll give me a second to have a sip of coffee anyway.